Right now, space itself stretches at 700,000 miles per hour, carrying galaxies away from us faster than light can travel. Every second, the universe grows larger than anyone can imagine, yet it expands into absolutely nothing. We journey through cosmic mysteries that shatter everything you think you know. Discover why every point in space believes it sits at the center of reality. Witness the invisible force that makes up 70% of existence, and confront the terrifying mathematics that predict our universe's final breath. If you're ready to have your mind completely blown, go ahead and hit that like button. Prepare yourselves. We begin. Space itself moves. Picture this cosmic truth that breaks your brain. Right now, the empty regions between galaxies stretch like invisible rubber. The distance from here to the nearest star grows larger every second. Space expands, carrying everything with it. You think empty space means nothing exists there. Wrong. Space represents the stage where physics plays out. It has properties. It bends near massive objects. It vibrates with gravitational waves. Most shocking of all, it grows. This challenges everything your mind wants to believe. When you blow up a balloon, the balloon expands into the room around it. The room provides space for the balloon to grow bigger, but our universe contains all the room there is. It expands without expanding into anything else. Think of it like this. Imagine you live on the surface of a balloon with no ability to see above or below. Your entire reality exists on that curved surface. As someone inflates the balloon, every point on the surface moves away from every other point. From your perspective, space itself grows. There is no outside for your two-dimensional world to expand into. Now, add one more dimension. We live in three-dimensional space that expands just like that balloon surface. The difference? We cannot perceive any dimension beyond our three. Space expands within itself, creating more space as it grows. Scientists call this intrinsic expansion. The universe does not push outward into some cosmic void. Space itself becomes larger. The measuring stick of reality stretches. This expansion happens everywhere at once. Between your atoms, the expansion force is too weak to overcome the electromagnetic forces holding you together. Between stars in our galaxy, gravity wins and keeps them bound. But between galaxy clusters, separated by millions of light years, nothing can stop the relentless growth of space. The numbers blow your mind. Every second, a region of space 1 million light years across grows by about 22 miles. That means galaxies millions of light years away race away from us at hundreds of thousands of miles per hour. Not because they move through space, but because space carries them along for the ride. Edwin Hubble first discovered this cosmic expansion in 1929. He found that every galaxy outside our local group moves away from us. The farther away they are, the faster they flee. This creates an illusion that we sit at the center of the universe. We do not. Every galaxy sees the same thing from their perspective. The expansion started 13.8 billion years ago, when space and time began. Since then, space has grown by a factor so large that astronomers struggle to measure it. A region that once measured smaller than an atom now spans billions of light years. However, Hubble discovered something even more disturbing about our expanding reality. Galaxies sprint away from Earth at impossible speeds. Edwin Hubble stared through the world's largest telescope in 1929, expecting to find a calm, static universe. Instead, he witnessed cosmic chaos. Every galaxy he studied raced away from our Milky Way like fleeing refugees. The faster they ran, the farther away they lived. This discovery shattered the scientific worldview. Einstein himself had assumed the universe remained fixed and unchanging for eternity. When his own equations predicted expansion, he added a mathematical fudge factor to keep everything static. He later called this his greatest mistake. Hubble measured galaxy speeds using a cosmic fingerprint technique. Every element in the universe produces light at specific colors when heated. Hydrogen glows red at a precise wavelength. Helium shines yellow at an exact frequency. These cosmic signatures never change. But Hubble found something impossible. The familiar hydrogen and helium signatures appeared stretched toward the red end of the spectrum. The farther away a galaxy sat, the more its light shifted red. This redshift revealed that galaxies moved away from us at tremendous speeds. The math told an incredible story. A galaxy 2 million light-years away moved at about 45 miles per second. A galaxy 4 million light-years distant fled at 90 miles per second. Double the distance, double the speed. This relationship held true everywhere Hubble looked. He called this pattern Hubble's law. It states that recession velocity equals distance multiplied by a number called the Hubble constant. Today we know that constant equals about 70 kilometers per second per megaparsec. In simpler terms, for every 3.25 million light-years of distance, galaxies race away 43 miles per second faster. The implications staggered astronomers. If everything moves away from everything else, then long ago, everything must have been much closer together. Trace the expansion backward in time, and all matter in the universe squeezes into an infinitely small point. This backward calculation led to the Big Bang theory. Hubble's discovery meant our universe has an age. Space itself began expanding 13.8 billion years ago from an unimaginably hot and dense state. Before that moment, neither space nor time existed as we understand them. The cosmic expansion explains why the night sky appears dark. If the universe were infinite, eternal, and static, then every direction you look should blaze with starlight. Instead, most of the universe remains invisible because light from distant regions has not had enough time to reach us yet. Even more disturbing, Hubble realized that galaxies farther than about 14 billion light-years flee faster than light itself can travel. These cosmic refugees cross the ultimate speed limit, disappearing beyond a horizon we can never penetrate. Modern telescopes have confirmed Hubble's findings with incredible precision. The James Webb Space Telescope has measured galaxy distances with accuracy better than 2%. Every observation supports the shocking truth that our universe expands relentlessly. But this raises a question that tortures physicists. If expansion happens everywhere, why does every galaxy think it sits at the center of the cosmic expansion? Every point in the universe believes it occupies the center of reality. Grab a deflated balloon and draw dots across its surface with a marker. Label each dot as a different galaxy. Now slowly inflate the balloon while watching what happens to your cosmic map. As the rubber stretches, every dot moves away from every other dot. The magic happens when you focus on any single dot. Pick the dot you labeled Milky Way. From this galaxy's perspective, all other dots race away in every direction. The Andromeda dot moves away. The Centaurus dot flees faster because it started farther away. Every galaxy appears to escape from your chosen center point. Here comes the mind-bending part. Move your attention to the Andromeda dot. From this new perspective, every other galaxy races away from Andromeda in all directions. The Milky Way dot moves away. The Centaurus dot still flees faster because of its greater distance. Andromeda now appears to sit at the center of cosmic expansion. This balloon demonstrates why Hubble's law works the same from every location. The expansion of space creates a situation where every observer sees themselves at the center of the universe. There is no preferred location, no special cosmic address. Every galaxy experiences identical expansion patterns. The balloon analogy reveals another crucial truth. The galaxies themselves do not move through space. The balloon material carries the dots along as it stretches. Similarly, space itself expands and carries galaxies along for the cosmic ride. Galaxies remain relatively stationary in their local patch of space, while space grows around them. This explains how galaxies can appear to move faster than light without violating Einstein's speed limit. The speed of light restriction applies to objects moving through space. It does not limit how fast space itself can grow. When space expands rapidly enough, it can carry distant galaxies away from us at superluminal speeds. Consider a galaxy 15 billion light-years away. Space between us and this distant galaxy expands at such a rate that it recedes at roughly 1.5 times the speed of light. The galaxy itself moves very slowly through its local space, but the expansion of intervening space creates the incredible recession velocity. The balloon model has limits. Real balloons expand into the surrounding room, but the universe expands into nothing. Real balloons have an inside and outside, but the universe contains all that exists. We must imagine a balloon with only its surface, where the inside and outside simply do not exist. Mathematicians call this type of expansion intrinsic rather than extrinsic. The balloon surface expands within itself without needing extra dimensions to expand into. Our three-dimensional space behaves the same way, growing larger without requiring a fourth spatial dimension. The expansion affects everything uniformly on the largest scales. From any galaxy, the cosmic expansion looks identical. Every civilization that develops astronomy will discover the same Hubble law. They will see the same pattern of galaxies fleeing in all directions. However, this uniform expansion began from a moment of unprecedented violence. Space and time erupted into existence from pure nothingness. 13.8 billion years ago, the universe measured smaller than the period at the end of this sentence. All the matter that would eventually form hundreds of billions of galaxies squeezed into a region tinier than a proton. The temperature reached 100 million trillion degrees. Physics breaks down when you try to understand conditions this extreme. Then expansion began. The first moment defies comprehension. There was no space for anything to expand into. There was no time for events to unfold within. The concepts of before and after had no meaning. Space and time themselves sprang into existence, along with all the matter and energy the universe would ever contain. Scientists call this moment the Big Bang, though the name misleads you. Picture a giant explosion hurling debris outward through empty space. That image captures nothing about what actually happened. Space itself began expanding, carrying protomatter along with it. No explosion occurred because there was nowhere for an explosion to happen. Within the first second, the universe underwent the most dramatic transformation in cosmic history. During a period called inflation, space expanded faster than anything science has ever measured. The universe grew by a factor of at least 1, followed by 26 zeros. In less time than light takes to cross a proton, regions that started smaller than atomic nuclei stretched to the size of basketballs. This inflation solves several cosmic puzzles. The universe appears remarkably uniform in all directions. Distant regions that could never have communicated with each other show identical temperatures and properties. Inflation explains this by stretching tiny, uniform patches of space to cosmic proportions. After inflation ended, the universe remained incredibly hot and dense. For the first 380,000 years, space glowed like the inside of a star. Free electrons scattered light in all directions, making the universe completely opaque. You could not see through this cosmic fog any more than you can see through the surface of the sun. Then came a moment astronomers call recombination. The expanding universe cooled enough for electrons to combine with atomic nuclei for the first time. Suddenly, light could travel freely through space. The universe became transparent, and the cosmic fog cleared forever. That ancient light still travels through space today. We call it the cosmic microwave background radiation. Every direction you look, this faint afterglow of creation fills the sky. It represents the oldest light in the universe, a baby picture taken when the cosmos was only 380,000 years old. The cosmic microwave background provides crucial evidence for the Big Bang theory. Its temperature matches predictions exactly. Tiny variations in this ancient light show where the first galaxies would eventually form. The pattern confirms that space has been expanding for nearly 14 billion years. Modern measurements reveal that the universe has expanded by a factor of about 1,100 since recombination, a region that measured 1 mile across when the cosmic microwave background was emitted. now spans over 1,000 miles. This expansion continues today at an ever-increasing rate. The Big Bang Theory makes a stunning prediction. If expansion started from an infinitely small point, then tracing the expansion backward should reveal when it began. Multiple independent methods confirm the universe is 13.8 billion years old, give or take about 20 million years. But expansion reveals an even stranger mystery when you examine how galaxies move through the growing cosmos. Galaxies behave like raisins in rising dough, carried apart by expanding space. Picture fresh bread dough studded with raisins sitting in a warm oven. As the dough rises, it doubles in size. The raisins do not move through the dough. Instead, the expanding dough carries them along, pushing each raisin away from every other raisin. A raisin that started 2 inches away from its neighbor now sits 4 inches away. This raisin bread analogy captures how cosmic expansion actually works. Galaxies represent the raisins. The invisible fabric of space represents the rising dough. As space expands, it carries galaxies along with it, increasing the distance between them without the galaxies actually moving. The analogy explains several puzzling features of cosmic expansion. First, galaxies do not fly through space at hundreds of thousands of miles per hour. They drift very slowly through their local regions, while space itself grows around them. Second, the expansion affects all distances equally. Just as every part of the bread dough rises at the same rate, every region of space expands at the same percentage rate. Here is where the numbers get wild. Space expands at a rate of about 70 kilometers per second per megaparsec. Break that cosmic mouthful down into simpler terms. For every 3.25 million light-years of distance, space grows by 43 miles every second. Double the distance, double the expansion rate. This means a galaxy 100 million light-years away recedes at about 1,300 miles per second. A galaxy 1 billion light-years distant flees at 13,000 miles per second. A galaxy 10 billion light-years away races away at 130,000 miles per second. The most distant observable galaxies retreat at nearly the speed of light. The raisin bread model reveals why distant galaxies appear to move so fast. Imagine measuring the distance between 2 raisins separated by the entire loaf of bread. As the dough doubles in size, those raisins end up twice as far apart. From one raisin's perspective, the other raisin moved at tremendous speed to reach its new position. Cosmic expansion works the same way. Between us and a distant galaxy lies billions of light-years of expanding space. Each small region expands slowly, but the cumulative effect across vast distances creates enormous recession velocities. The galaxy itself barely moves. The expansion of intervening space accounts for nearly all its apparent motion. This explains how galaxies can appear to exceed light speed without violating physics. Einstein's speed limit applies to motion through space, not to the expansion of space itself. When space expands fast enough, it can carry objects apart at superluminal speeds. The raisin bread analogy breaks down in one important way. Bread dough expands into the surrounding oven space. The universe has no surrounding space to expand into. Space creates more space as it grows, like magical dough that conjures its own oven. Astronomers can measure this expansion directly by observing how light changes as it travels through growing space. Galaxies flee faster than light can travel, yet Einstein's cosmic speed limit remains unbroken. 14 billion light-years away, a galaxy races away from us at nearly 200,000 miles per second. Light travels at 186,000 miles per second. Simple math reveals this galaxy exceeds the universal speed limit by 14,000 miles per second. How does this apparent violation of physics occur? The answer lies in understanding what Einstein actually prohibited. His special theory of relativity forbids any object from accelerating past light speed through space. Nothing with mass can reach 670 million miles per hour relative to its local surroundings. This rule remains absolutely inviolate throughout the universe. However, Einstein never restricted how fast space itself could grow. When space expands, it creates more space between objects without moving the objects through space. Picture two ants walking slowly across an inflating balloon. Each ant moves at a crawl across the rubber surface. Yet, as the balloon inflates, the distance between them increases much faster than either ant can walk. Cosmic expansion works identically. Galaxies drift slowly through their local patches of space, typically at speeds of a few hundred miles per second. Meanwhile, space itself expands around them, carrying them apart at velocities that can exceed light speed for sufficiently distant objects. The galaxies never violate Einstein's speed limit because they barely move through space at all. This creates a cosmic horizon beyond which we can never see. Any galaxy receding faster than light cannot send us signals. Its light travels toward us at 186,000 miles per second, but space expansion carries the galaxy away faster than its light can approach. The light makes progress initially, but the expanding space between us eventually overwhelms the light's forward motion. The mathematics reveal the exact distance of this cosmic horizon. Any galaxy farther than approximately 14 billion light-years recedes faster than light. We call this distance the Hubble horizon. Beyond this boundary, galaxies become fundamentally unobservable. They exist, but we can never detect their light or communicate with them. Even stranger, galaxies we can see today will eventually disappear beyond this horizon. As expansion accelerates, more and more galaxies will cross the boundary between observable and unobservable. In the far future, our descendants will see a much emptier universe as distant galaxies vanish from view one by one. The superluminal recession of distant galaxies affects the light we do receive from closer objects. Consider light emitted by a galaxy 8 billion light-years away. When this light began its journey toward us 8 billion years ago, the galaxy was much closer. Expansion has since carried it to a much greater distance. During its 8 billion-year journey, this light traveled through continuously expanding space. The expansion stretched the light waves themselves, increasing their wavelength and reducing their energy. Blue light becomes green. Green light becomes red. Red light becomes infrared. This stretching effect increases with distance, making the most distant observable galaxies appear extremely red. Astronomers call this phenomenon cosmological redshift. Unlike the Doppler redshift caused by motion through space, cosmological redshift results from the expansion of space itself during the light's journey. The amount of redshift directly reveals how much the universe has expanded since the light was emitted. The most distant galaxies show redshifts so extreme that their ultraviolet light arrives as infrared radiation. This cosmic stretching of light provides direct evidence for the ongoing expansion of space itself. Yet this expansion has limits we can observe, creating a cosmic prison from which no information can escape. Light from the edge of reality took 46 billion years to reach your eyes, yet the universe is only 13.8 billion years old. This cosmic paradox emerges from the interplay between light speed and space expansion. When you look at distant galaxies, you see them as they were billions of years ago when their light began its journey toward Earth. The most distant observable objects appear as they were when the universe was only 380,000 years old. That ancient light has traveled for 13.8 billion years to reach us. Logic suggests these distant objects should be 13.8 billion light-years away. Wrong. Space expansion during the light's journey carried those objects much farther away. Today, they sit approximately 46 billion light-years from Earth. This creates our observable universe, a cosmic sphere with Earth at the center and a radius of 46 billion light-years. Everything within this sphere remains potentially visible to us. Everything beyond it lies forever hidden. The observable universe contains all the galaxies, stars, and matter we can ever hope to detect, no matter how powerful our telescopes become. The boundary of the observable universe represents the ultimate horizon. No information from beyond this edge can ever reach us. These distant regions might contain incredible civilizations, impossible physics, or even other universes. We will never know. The expansion of space ensures that this cosmic censorship remains absolute. The observable horizon affects what we can learn about the universe's structure. If the universe extends beyond our observable region, we cannot determine its true size or shape. The cosmos might be infinite, or it might curve back on itself like the surface of a sphere. Regions beyond our horizon hold these secrets forever. Even more disturbing, the observable universe shrinks in terms of the number of galaxies we can see. As expansion accelerates, galaxies near the edge of observability recede faster and faster. Eventually, they cross the threshold where space carries them away faster than light can travel. Their light can no longer reach us, and they disappear from our universe forever. Current observations suggest that approximately 2 trillion galaxies populate our observable universe. Each galaxy contains hundreds of billions of stars. The total number of stars within our cosmic horizon exceeds the number of grains of sand on all Earth's beaches by a factor of millions. Yet, this represents only a tiny fraction of what might exist beyond the horizon. The horizon also limits how far into the past we can observe. The cosmic microwave background radiation represents the oldest light in the universe, emitted when space became transparent 380,000 years after the Big Bang. Before this moment, the universe remained opaque to light. We cannot see directly into the epoch when space and time began. This creates a fundamental limit to astronomical observation. No optical telescope, no matter how advanced, can peer beyond the cosmic microwave background. To study earlier times, scientists must use other methods, such as gravitational wave detection or theoretical modeling. The observable horizon moves outward at the speed of light, revealing new regions of space every second. However, expansion carries distant matter away faster than the horizon expands. This means the number of galaxies within our observable universe actually decreases over time, despite the horizon growing larger. In the distant future, our descendants will inhabit a much lonelier cosmos. One by one, distant galaxies will vanish beyond the horizon. Only our local group of gravitationally bound galaxies will remain visible. The universe will appear to contain just a few dozen galaxies instead of trillions. This expanding light carries with it a stretched signature that reveals the universe's deepest secret. Photons stretch like cosmic taffy during their billion-year journeys through expanding space. Imagine a wave drawn on a deflated balloon. As you inflate the balloon, the wave stretches. Its peaks spread farther apart. Its wavelength increases. Light traveling through expanding space behaves identically. The relentless growth of space stretches photon wavelengths during their cosmic voyages. This stretching effect creates one of astronomy's most powerful tools. When light leaves a distant galaxy, it carries the precise electromagnetic signatures of hydrogen, helium, and other elements. These spectral lines appear at specific wavelengths that never change. Hydrogen always produces a bright red line at 656 nanometers. Helium creates a yellow line at 588 nanometers. However, when this ancient light finally reaches Earth, after traveling billions of years, astronomers discover something impossible. The familiar hydrogen line no longer glows red at 656 nanometers. Instead, it appears at 700 nanometers, shifted toward the infrared. The helium line moves from yellow to orange. Every spectral signature stretches to longer, redder wavelengths. Scientists call this phenomenon cosmological redshift. It differs completely from the Doppler redshift you experience when an ambulance passes by. Doppler shift occurs when the source moves through space, toward or away from you. Cosmological redshift happens because space itself expands during the light's journey, stretching the waves like rubber bands. The amount of redshift directly reveals how much the universe has expanded since the light was emitted. A redshift of 1 means the universe has doubled in size. A redshift of 2 indicates the cosmos has tripled. The most distant observable galaxies show redshifts exceeding 10, meaning the universe has grown more than 11 times larger since their light began its journey toward us. This cosmic stretching affects different types of light in dramatic ways. Ultraviolet light from distant galaxies arrives on Earth as visible light. Visible light becomes infrared. Infrared radiation stretches into radio waves. X-rays from ancient quasars reach us as ordinary visible light. The James Webb Space Telescope specifically observes in infrared wavelengths to capture the stretched light from the universe's earliest galaxies. Redshift measurements allow astronomers to calculate precise distances to remote galaxies. The greater the redshift, the farther away the galaxy sits today. This technique works because expansion affects all of space uniformly. A galaxy with twice the redshift of another galaxy is approximately twice as distant. The cosmic stretching of light also reduces its energy. High-energy gamma rays from distant supernovas arrive as low-energy radio waves. This energy reduction means that ancient light appears much dimmer than it was when emitted. The most distant galaxies shine with the apparent brightness of candles viewed from thousands of miles away, even though they actually blaze brighter than 1 trillion suns. Astronomers have measured redshifts for millions of galaxies, creating a three-dimensional map of cosmic structure. These measurements reveal how matter clumped together over billions of years to form the galaxies and galaxy clusters we see today. The redshift surveys show that expansion affects empty space between galaxy clusters while having little effect on regions where gravity binds matter together. The most extreme redshifts come from the cosmic microwave background radiation. This ancient light shows a redshift of about 1,100, indicating that the universe has expanded by this factor since the light was emitted 380,000 years after the Big Bang. This radiation originally glowed as bright visible light from the hot cosmic plasma. Expansion has stretched it into faint microwave radiation. However, recent precision measurements of cosmic redshift have revealed a disturbing mystery that threatens our understanding of the universe. A mysterious force, stronger than gravity, drives the universe apart at an accelerating rate. In 1998, two teams of astronomers made a discovery that changed physics forever. They expected to find that cosmic expansion was slowing down. Gravity from all the matter in the universe should gradually break the expansion that began with the Big Bang. Instead, they found the opposite. Expansion is speeding up. This acceleration defied every prediction. For nearly 14 billion years after the Big Bang, gravity did indeed slow the cosmic expansion. Galaxy clusters formed as matter clumped together under its attractive influence. The expansion rate decreased steadily. Then, about 5 billion years ago, something changed. An unknown force began overpowering gravity on the largest scales. Scientists named this mysterious phenomenon dark energy. The name reflects our complete ignorance about its nature. We cannot see it, touch it, or detect it directly. Yet this invisible force dominates the entire universe. It drives the acceleration that will ultimately determine the cosmos's final fate. The evidence for dark energy comes from studying ancient stellar explosions called Type Ia supernovas. These cosmic bombs all explode with nearly identical brightness, making them perfect cosmic distance markers. By measuring their apparent brightness, astronomers can calculate exactly how far away they are. By measuring their redshift, astronomers determine their recession velocity. When researchers plotted supernova distances against their redshifts, they expected to see a straight-line relationship matching Hubble's law. Instead, they found that distant supernovas appeared dimmer than expected. This meant they were farther away than simple expansion models predicted. Something had accelerated the expansion, carrying these ancient galaxies to greater distances than anticipated. The acceleration appears to affect only the vast, empty regions between galaxy clusters. Within galaxy clusters, where matter density remains high, gravity still dominates. Dark energy cannot overcome the gravitational binding that holds galaxies together. It only influences regions where matter density drops below a critical threshold. This selective influence creates a bizarre cosmic landscape. Galaxy clusters remain gravitationally bound islands in an ocean of accelerating expansion. The empty space between clusters grows at an ever-increasing rate. Future civilizations living in these island galaxies will see an increasingly empty universe as distant clusters disappear beyond their cosmic horizon. Current observations suggest that dark energy makes up about 68% of the total energy content of the universe. Ordinary matter, including all stars, planets, and living beings, accounts for less than 5%. Dark matter, another mysterious component, comprises about 27%. This means that 95% of reality consists of phenomena we do not understand. The nature of dark energy remains one of physics's greatest mysteries. Some theories propose it represents the energy of empty space itself, arising from quantum fluctuations in the vacuum. Other models suggest it emerges from extra dimensions beyond the three spatial dimensions we perceive. Still others argue that dark energy changes over time, growing stronger or weaker as the universe evolves. Recent observations from the Dark Energy Spectroscopic Instrument suggest that dark energy might indeed be evolving. If confirmed, this discovery would revolutionize cosmology. It would mean that the mysterious force driving cosmic acceleration is not constant, opening possibilities for new physics beyond our current theories. The consequences of dark energy extend far into the future. If it continues strengthening, expansion will accelerate until it tears apart all gravitationally bound structures. First, galaxy clusters will disperse. Then, individual galaxies will dissolve. Eventually, even atoms might split apart in an event called the Big Rip. However, the true nature of dark energy continues to perplex scientists because it appears to dominate the universe, yet remains completely invisible. The universe consists mostly of a substance that defies detection, yet its effects dominate reality. Picture the cosmic inventory. Count every star in every galaxy. Add all the planets, moons, asteroids, and interstellar gas. Include every black hole, neutron star, and exotic object astronomers have discovered. Weigh all the matter that makes up the structures we observe throughout the universe. This entire collection represents less than 5% of what actually exists. The remaining 95% consists of two mysterious components that interact with ordinary matter only through gravity. Dark matter accounts for 27% of the cosmic budget. Dark energy makes up the final 68%. Neither component emits light or responds to electromagnetic forces. They remain invisible to every instrument we possess. Dark energy presents the greater mystery. Unlike dark matter, which at least clumps together and helps form cosmic structures, dark energy appears perfectly uniform throughout space. It shows no variation from one region to another. It does not cluster around galaxies or accumulate in dense clouds. Instead, it fills every cubic inch of space with identical density. This uniformity creates dark energy's most puzzling property. As the universe expands and space grows larger, the total amount of dark energy increases proportionally. Double the volume of space, and you double the amount of dark energy. This violates our normal experience with energy conservation. When you stretch a rubber band, its elastic energy increases, but the total energy remains constant. Dark energy apparently creates more energy as space expands. The energy density of dark energy is remarkably small. Each cubic yard of empty space contains dark energy equivalent to about 6 hydrogen atoms worth of mass. This seems insignificant until you consider the vast volume of the universe. The total dark energy within our observable universe exceeds the mass energy of all visible matter by more than 10 times. Scientists have proposed several candidates for dark energy. The leading theory suggests it represents the energy of empty space itself, arising from quantum mechanical effects. Quantum physics predicts that empty space seeds with virtual particles that pop into existence and disappear faster than light can cross an atomic nucleus. This quantum foam might create a constant energy density throughout space. However, quantum calculations predict a dark energy density that exceeds observations by a factor of 10, followed by 120 zeros. This represents the worst prediction in the history of physics. Either quantum mechanics is fundamentally wrong, or dark energy has a completely different origin. Alternative theories propose that dark energy emerges from extra dimensions beyond the 3 spatial dimensions we perceive. In these models, gravity leaks into higher dimensions on cosmic scales, creating apparent acceleration without requiring mysterious energy. Other proposals suggest that dark energy is not constant, but changes over time, growing stronger or weaker as the universe evolves. Recent observations from multiple cosmic surveys hint that dark energy might indeed be evolving. The Dark Energy Spectroscopic Instrument has measured tiny variations in dark energy's behavior over cosmic time. If confirmed, this would require completely new physics to explain how and why dark energy changes. The dominance of dark energy means that ordinary matter plays only a minor role in the universe's ultimate fate. Stars, galaxies, and everything made of atoms represent cosmic afterthoughts in a universe controlled by invisible forces. The matter that forms our bodies, our planet, and all life emerged from the 5% of reality that we can actually observe and understand. This cosmic composition creates a humbling perspective on humanity's place in the universe. We are made of rare stuff in a cosmos dominated by phenomena we cannot detect or comprehend. Our entire visible universe, including billions of galaxies and countless stars, represents a tiny minority of what actually exists. Yet, recent precision measurements have revealed an even more disturbing problem with our understanding of cosmic expansion. 2 methods for measuring cosmic expansion produce different answers, threatening the foundation of modern cosmology. The crisis began with precision. As telescopes improved and measurements became more accurate, astronomers expected their calculations of the expansion rate to converge on a single definitive answer. Instead, they discovered a disturbing discrepancy that refuses to disappear. 2 completely independent methods for measuring the Hubble constant disagree by about 9%. This 9% difference might seem trivial. It is not. Both measurement techniques achieve precision better than 2%. The disagreement far exceeds the margin of error for either method. Something is fundamentally wrong with our understanding of cosmic expansion. The first method studies the cosmic microwave background radiation, the afterglow of the Big Bang. This ancient light carries detailed information about the universe when it was only 380,000 years old. By analyzing tiny temperature fluctuations in this primordial glow, cosmologists can calculate how fast the universe expands today. This technique yields a Hubble constant of about 67 kilometers per second per megaparsec. The second method measures distances to nearby galaxies using pulsating stars called Cepheid variables. These stellar lighthouses change brightness in regular cycles that directly relate to their absolute luminosity. By comparing their apparent brightness to their known luminosity, astronomers can calculate their distance with remarkable precision. This local measurement technique produces a Hubble constant of about 73 kilometers per second per megaparsec. The 6-unit discrepancy between these values represents a crisis in cosmology. If the cosmic microwave background measurement is correct, then distant galaxies should appear closer than they actually do. If the local measurement is correct, then our models of the early universe must be wrong. Either way, our understanding of cosmic expansion contains a fundamental flaw. Adam Rees, who won the Nobel Prize for discovering dark energy, leads the team making local measurements. His group has refined their techniques over decades, checking for systematic errors and improving their precision. They consistently find the higher value of 73. The cosmic microwave background analysis performed by the Planck satellite mission consistently produces the lower value of 67. Multiple independent teams have confirmed both measurements using different techniques. Some groups study type Ia supernovas instead of Cepheid variables. Others use gravitational lensing effects or surface brightness fluctuations. The local measurements consistently cluster around 73. The early universe measurements consistently favor 67. This Hubble tension suggests that something significant happened in cosmic history that our standard model fails to account for. Perhaps dark energy behaved differently in the past. Maybe unknown particles influenced the expansion during the universe's first few billion years. Some theories propose that space itself has properties we have not discovered. The implications extend far beyond academic curiosity. The Hubble constant determines the age of the universe, the distances to galaxies, and the ultimate fate of cosmic expansion. If we cannot measure this fundamental parameter correctly, then our entire cosmological framework stands on shaky ground. Recent attempts to resolve the tension have only deepened the mystery. Some researchers propose that local measurements suffered from systematic errors. Others suggested that cosmic microwave background analysis made incorrect assumptions. Independent checks have largely ruled out both possibilities. The James Webb Space Telescope entered this controversy with the potential to settle the debate once and for all. Its unprecedented precision and sensitivity promised to resolve the Hubble tension definitively. Instead, Webb's observations have made the mystery even more perplexing. The most powerful telescope ever built validates the measurements that break our understanding of the universe. Scientists hoped that the James Webb Space Telescope would solve the Hubble tension by revealing flaws in previous observations. Instead, Webb delivered the most precise confirmation yet that our cosmological models are incomplete. The discrepancy in expansion rate measurements is real, persistent, and demands new physics to explain. Webb's infrared vision penetrates cosmic dust clouds that blocked Hubble's view, revealing Cepheid variable stars with unprecedented clarity. These pulsating giants serve as cosmic distance markers, and Webb can observe them in galaxies up to 130 million light-years away. The telescope's measurements agree with Hubble's findings to within 1%, confirming that local expansion rate measurements are not the result of systematic errors. The precision of Webb's observations eliminates most remaining doubt about the Hubble tension. Two flagship NASA telescopes, using completely independent measurement techniques, now both confirm that the universe expands at 73 kilometers per second per megaparsec in our local cosmic neighborhood. This value exceeds predictions based on the early universe by 9%. Webb's data comes from the largest sample of cosmic distance measurements ever assembled. The telescope studied over 300 Cepheid variables in nearby galaxies, cross-checked with carbon-rich stars and surface brightness fluctuations. Multiple independent techniques all converge on the same answer. The local expansion rate significantly exceeds early universe predictions. This confirmation forces astronomers to confront uncomfortable possibilities about the nature of cosmic expansion. Either our understanding of the early universe is fundamentally flawed, or unknown physics influences expansion in ways we have never imagined. Both options require revising the standard model of cosmology that has successfully explained countless observations for decades. The Webb data reveals subtle patterns that may point toward solutions. The telescope detects tiny variations in expansion rate across different directions in space. Some regions appear to expand slightly faster than others, hinting that dark energy might not be perfectly uniform. These variations are small, but they challenge the assumption that cosmic expansion is completely isotropic. Webb's observations also extend farther into the past than previous measurements. The telescope can observe Cepheid variables in galaxies whose light has traveled for over 100 million years to reach us. This extended baseline allows astronomers to trace how the expansion rate has changed over cosmic time, providing new constraints on dark energy behavior. The implications of Webb's confirmation extend throughout cosmology. If the higher expansion rate is correct, then the universe is about 1 billion years younger than previously calculated. This age revision affects models of galaxy formation, stellar evolution, and the development of cosmic structure. It also changes calculations of dark energy density and the ultimate fate of the universe. Nobel laureate Adam Rees, who leads the team making these precision measurements, describes the situation as both a challenge and an incredible opportunity. The discrepancy suggests that our understanding of the universe may be incomplete, pointing toward discoveries of new physics that could revolutionize cosmology. Several exotic theories attempt to explain the Hubble tension. Early dark energy models propose that a mysterious force influenced expansion during the universe's first few billion years before disappearing. Extra dimensions theories suggest that gravity behaves differently on cosmic scales than predicted by Einstein's general relativity. Some models invoke interactions between dark matter and dark energy that change over cosmic time. Webb's conformation also affects practical astronomy. Precise distance measurements depend on accurate knowledge of the expansion rate. The Hubble tension introduces uncertainty into calculations of galaxy distances, supernova luminosities, and the three-dimensional structure of the universe. This uncertainty propagates through numerous astronomical studies. The resolution of the Hubble tension may require observations that go beyond electromagnetic radiation to probe the deepest structure of cosmic expansion. The universe's baby photo reveals the moment space became transparent and expansion began slowing down. 380,000 years after the Big Bang, the cosmos flashed like a cosmic camera bulb. For the first time since creation began, space became transparent to light. This ancient illumination still fills the universe today, carrying detailed information about cosmic expansion from when the universe was less than 1% of its current age. Before this moment, space remained completely opaque. The universe was so hot and dense that electrons could not attach to atomic nuclei. Free electrons scattered light in all directions, making the cosmos as opaque as the inside of a star. You could not see more than a few inches through this cosmic fog, no matter how powerful your eyes might be. Then the universe cooled to 3,000 degrees. Suddenly, electrons combined with protons and helium nuclei to form the first stable atoms. Light could finally travel freely through space. The cosmic fog cleared in an instant that astronomers call recombination. The entire universe became transparent simultaneously. The light emitted during recombination has traveled through space for 13.4 billion years to reach us today. Cosmic expansion has stretched these ancient photons from visible wavelengths to microwave radiation. This cosmic microwave background now bathes every cubic inch of the universe in faint radio waves with a temperature of -454 degrees Fahrenheit. The cosmic microwave background appears remarkably uniform in all directions. Its temperature varies by less than 1 part in 100,000 across the entire sky. This uniformity initially puzzled astronomers. Regions of space separated by billions of light years show identical temperatures, yet they could never have communicated with each other at the speed of light. Cosmic inflation solves this puzzle. During the first fraction of a second after the Big Bang, space expanded much faster than light could travel. This rapid expansion stretched tiny, uniform regions to cosmic proportions. Areas that started in thermal equilibrium were carried far apart by inflation, maintaining their identical temperatures across vast distances. Tiny temperature fluctuations in the cosmic microwave background reveal where the first galaxies would eventually form. Slightly warmer regions contained slightly more matter. Over millions of years, gravity amplified these tiny density differences into the galaxies and galaxy clusters we observe today. The cosmic microwave background provides a blueprint for all large-scale structure in the universe. Precise measurements of these temperature patterns allow cosmologists to determine fundamental properties of the universe with remarkable accuracy. The geometry of space appears flat to within 1%. The age of the universe is 13.7 billion years, plus or minus 20 million years. Dark matter comprises 26.8% of cosmic density, while dark energy accounts for 68.3%. These measurements also determine the expansion rate of the universe at recombination. By combining this ancient expansion rate with models of how expansion has changed over cosmic time, cosmologists calculate that space should expand at 67 kilometers per second per megaparsec today. This prediction disagrees with direct local measurements by 9%. The cosmic microwave background analysis depends critically on understanding how cosmic expansion has evolved over 13.8 billion years. Small changes in the expansion history produce measurable differences in the temperature patterns we observe today. The standard model of cosmology, including dark matter and dark energy, successfully explains these observations with extraordinary precision. However, the model fails to predict the expansion rate that telescopes measure in our local cosmic neighborhood. This failure suggests that either the cosmic microwave background analysis contains subtle errors, or the standard model omits important physics that affects cosmic expansion. Recent observations from the Planck satellite have refined cosmic microwave background measurements to their practical limits. The temperature patterns have been mapped with precision that exceeds 1 part in a million. These incredibly detailed observations confirm the standard model's predictions, while simultaneously highlighting the tension with local expansion rate measurements. The cosmic microwave background represents our deepest view into cosmic history, but it cannot probe the universe's first 380,000 years, when space remained opaque to light. In less than 1/trillionth of a trillionth of a trillionth of a second, space expanded faster than anything science has ever measured. Before the cosmic microwave background, before atoms formed, before space became transparent, the universe underwent the most violent expansion in cosmic history. This period, called cosmic inflation, lasted shorter than the time light takes to cross a proton. Yet during this incomprehensibly brief moment, space grew by a factor larger than the number of atoms in the observable universe. Picture a region smaller than a subatomic particle, containing all the matter and energy that would eventually form billions of galaxies. Then imagine this tiny volume inflating to the size of a grapefruit in less time than a photon takes to vibrate once. This represents the minimum expansion that inflation theory requires. The actual expansion may have been vastly larger. Alan Guth proposed cosmic inflation in 1980 to solve several puzzles about the Big Bang theory. The universe appears remarkably flat and uniform, yet regions separated by billions of light years could never have communicated at light speed. Inflation solves this by expanding tiny, uniform patches of space to cosmic proportions faster than light could travel between them. The inflation field that drove this expansion remains hypothetical. Scientists call it the inflaton, but nobody knows what it actually was. This mysterious field filled space with enormous energy density, causing space itself to expand at exponential rates. The inflaton field eventually decayed, converting its energy into the hot plasma that filled the early universe. During inflation, space expanded so rapidly that quantum fluctuations were stretched to macroscopic scales. These tiny energy differences became the seeds for all cosmic structure. Without inflation, the universe would be perfectly smooth and uniform. No galaxies, stars, or planets could ever have formed. The mathematics of inflation boggle the mind. If inflation lasted just 60 e-foldings, meaning space doubled in size 60 times, the universe would grow by a factor of 1 followed by 18 zeros. Most inflation models predict hundreds of e-foldings, creating expansion factors that exceed the number of particles in the visible universe. This incredible expansion explains why space appears geometrically flat, just as the surface of a balloon appears flat when inflated to enormous size. Cosmic inflation stretched space until its curvature became undetectable. Any initial curvature was diluted away by the exponential expansion. Inflation also explains the cosmic microwave background's near-perfect uniformity. Regions that appear separated by billions of light years today actually originated from the same tiny patch of space before inflation began. They shared identical properties before being carried apart faster than light could travel between them. The end of inflation triggered a process called reheating. The inflaton field decayed into elementary particles, filling space with the hot, dense plasma that characterizes the traditional Big Bang model. This reheating phase created all the matter and radiation that we observe in the universe today. Evidence for inflation comes from precise measurements of cosmic microwave background temperature fluctuations. These patterns match predictions of how quantum fluctuations would appear after being stretched by exponential expansion. The agreement between theory and observation provides strong support for the inflation paradigm. However, inflation remains theoretical because we cannot observe it directly. The cosmic microwave background formed 380,000 years after inflation ended. Everything about the inflation epoch must be inferred from its consequences rather than direct observation. Recent observations suggest that inflation may have left detectable traces in the form of gravitational waves rippling through space-time. These primordial gravitational waves would create distinctive patterns in cosmic microwave background polarization that future telescopes might detect. The implications of inflation extend far beyond explaining cosmic uniformity, potentially revealing the ultimate geometry of everything that exists. The universe has one of three possible shapes, and only one of them allows infinite expansion forever. Reality itself has geometry. Just as you can bend a piece of paper into different shapes, the fabric of space-time can curve in ways that determine the ultimate fate of cosmic expansion. Three possibilities exist, each leading to a dramatically different future for everything that exists. A flat universe extends infinitely in all directions with zero curvature. Parallel lines remain parallel forever. The angles of any triangle add up to exactly 180 degrees. In flat geometry, expansion continues forever, but gradually slows to nearly zero velocity. Galaxies drift apart for eternity, approaching but never quite reaching a final separation distance. Picture this flat reality like an infinite sheet of paper. Draw parallel lines across it, and they never meet. Measure any triangle, and its angles always sum to 180 degrees. This represents the three-dimensional cosmic equivalent of flat Euclidean geometry that we experience in everyday life. A closed universe curves back on itself, like the surface of a sphere. Parallel lines eventually meet, just as lines of longitude converge at Earth's poles. Triangles have angles that sum to more than 180 degrees. In closed geometry, expansion eventually reverses. The universe contracts back to a singularity in a big crunch that mirrors the Big Bang. Imagine walking in a straight line across the surface of a giant sphere. Eventually, you return to your starting point even though you never turned. The universe appears infinite from your limited perspective, but it actually has finite volume. In a closed universe, space curves back on itself in three dimensions the same way. An open universe curves away from itself like a saddle. Parallel lines diverge rather than remaining parallel. Triangle angles sum to less than 180 degrees. Open geometry leads to eternal, accelerating expansion. Galaxies flee from each other forever at ever-increasing speeds until the universe becomes cold, dark, and empty. Think of a saddle-shaped surface where parallel lines drawn across it spread apart. The negative curvature causes expansion to accelerate indefinitely. In an open universe, cosmic acceleration never stops. Expansion continues until it rips apart every gravitationally bound structure. The amount of matter and energy in the universe determines which geometry describes reality. High density curves space into closed geometry. Low density creates open geometry. A precise critical density produces perfectly flat geometry. This critical density equals about 6 protons worth of mass per cubic yard of space. Current observations indicate that our universe sits remarkably close to this critical density. Measurements of cosmic microwave background temperature fluctuations show that space has flat geometry to within 1% accuracy. The universe appears balanced on the knife's edge between open and closed possibilities. This near-perfect flatness puzzled cosmologists for decades. Why should the density be so precisely tuned to produce flat geometry? Cosmic inflation provides the answer. Exponential expansion during the first fraction of a second stretched any initial curvature until it became undetectable, just like inflating a balloon until its surface appears flat. However, dark energy complicates this geometric picture. Even in a flat universe, the acceleration caused by dark energy can overwhelm the gradual deceleration that flat geometry normally produces. Instead of expanding forever at decreasing rates, our flat universe expands forever at increasing rates because dark energy dominates over matter. The ultimate fate of expansion depends on whether dark energy remains constant or changes over time. If dark energy grows stronger, it could eventually overpower all other forces in the universe. If dark energy weakens, cosmic expansion might slow down or even reverse despite the flat geometry. Recent precision measurements reveal that determining the universe's exact geometry requires understanding why cosmic expansion balances so perfectly at the critical density. The universe contains exactly the right amount of matter to balance expansion between eternal growth and eventual collapse. 6 protons worth of mass in every cubic yard of space. This represents the critical density that separates universes that expand forever from those that eventually contract back into singularities. Add slightly more matter, and gravity overcomes expansion, leading to a big crunch. Include slightly less matter, and expansion accelerates without limit, creating a cold, empty cosmos. Our universe sits within 1% of this critical value. This incredible fine-tuning puzzled cosmologists for decades. Why should the cosmic density be so precisely calibrated? The universe could have contained 1,000,000 times more matter or 1,000,000,000 times less. Instead, it hovers at exactly the boundary between expansion and collapse. The critical density emerges from the competition between 2 cosmic forces. Gravity tries to pull everything together, slowing the expansion that began with the Big Bang. The initial expansion velocity pushes everything apart, working against gravity's attractive influence. The critical density represents the exact balance point between these opposing forces. Think of throwing a ball upward from Earth's surface. Throw it too slowly, and gravity pulls it back down. Throw it faster than 25,000 miles per hour, and it escapes Earth's gravitational influence forever. The escape velocity represents the critical speed that balances gravitational attraction against kinetic energy. Cosmic expansion works similarly, with the critical density determining whether the universe expands forever or collapses. This cosmic coincidence becomes even more mysterious when you consider how density has changed over time. In the early universe, matter density was much higher than the critical value. As space expanded, matter spread out and its density decreased. Meanwhile, the critical density also decreased as expansion slowed down. These 2 values evolved together, maintaining their near equality for billions of years. The probability of this cosmic coincidence occurring by chance approaches 0. If the initial density had differed from critical by even 1 part in a billion, the universe would have either collapsed within minutes of the Big Bang or expanded so rapidly that no structures could ever have formed. Neither scenario permits the existence of galaxies, stars, planets, or life. Cosmic inflation provides one explanation for this fine-tuning. During the exponential expansion that occurred in the first fraction of a second after the Big Bang, any deviation from critical density was diluted away. Inflation drove the cosmic density to exactly the critical value, regardless of what it was initially. However, dark energy complicates this picture. While matter and radiation densities decrease as the universe expands, dark energy density remains constant. This means that dark energy becomes increasingly dominant over time, eventually overwhelming both matter and the critical density balance. Today, dark energy accounts for about 68% of the cosmic density. Matter contributes only about 32%. This means the total density actually exceeds the critical value, but dark energy's repulsive effect dominates over matter's gravitational attraction. The universe expands at an accelerating rate despite having supercritical density. The critical density mystery connects to fundamental questions about the nature of physical reality. Why do the constants of physics have the values they do? Why is the universe structured in a way that permits complex chemistry and biology? The critical density represents one of many cosmic coincidences that appear necessary for our existence. Some physicists propose that multiple universes exist with different physical properties. In this multiverse scenario, we observe a universe with critical density simply because we could not exist in universes with wildly different densities. This anthropic reasoning explains the coincidence by selection effects rather than fundamental physics. Alternative theories suggest that the critical density balance emerges from deeper physical principles we have not yet discovered. Perhaps quantum gravity effects or extra dimensions naturally drive cosmic density toward the critical value. These ideas remain speculative, but point toward new physics beyond our current understanding. Recent observations hint that our understanding of critical density may be incomplete, as radical new theories propose that cosmic expansion has entirely different origins. Our universe expands because it constantly absorbs smaller parallel realities in cosmic collisions we cannot detect. Forget dark energy. A radical new theory suggests that cosmic acceleration happens because our universe keeps merging with tiny baby universes that pop into existence around us. These collisions inject additional space into our reality, causing the expansion we observe without requiring mysterious, invisible forces. Jan Ambjørn, a physicist at Copenhagen University, proposed this startling idea to explain why expansion accelerates without invoking dark energy. In his model, quantum fluctuations constantly create microscopic universes throughout space. Our larger universe absorbs these baby realities, growing bigger with each collision. Picture soap bubbles forming in a bathtub. Small bubbles constantly merge with larger ones, making the big bubbles grow. In Ambjørn's theory, our universe represents the largest bubble in a cosmic foam of realities. Baby universes merge with ours like quantum soap bubbles, adding their volume to our expanding space. These baby universes remain completely invisible to us. They exist in higher dimensions, beyond the 3 spatial dimensions we can perceive. We cannot detect them directly because they interact with our reality only through gravitational effects. The merging process appears to us as cosmic expansion, driven by mysterious dark energy. The mathematics work remarkably well. When Ambjørn calculated the expansion rate that baby universe mergers should produce, the result matched observations more accurately than standard dark energy models. The theory explains cosmic acceleration without requiring 95% of the universe to consist of invisible substances we cannot detect or understand. Baby universe creation connects to fundamental quantum mechanics. According to quantum field theory, empty space seethes with virtual particles that appear and disappear faster than light can cross an atomic nucleus. Some theories suggest that these quantum fluctuations can create actual pocket universes under extreme conditions. The baby universes start incredibly tiny, smaller than protons, but they grow rapidly after birth. Most remain microscopic and merge with our universe almost immediately. Others might grow larger and develop their own physical laws before eventually joining our reality. The merger process happens continuously throughout space and time. This constant absorption of baby universes could explain several cosmic mysteries beyond dark energy. It might account for why space appears flat despite containing matter that should curve it. The influx of new space from mergers could dilute cosmic curvature, maintaining flat geometry indefinitely. The theory also addresses the cosmic coincidence problem. Why does our universe have exactly the right properties to support complex structures like galaxies and stars? If multiple baby universes with different properties constantly merge with ours, The most successful combinations would dominate over time through a kind of cosmic natural selection. However, the baby universe theory remains highly speculative. We have no direct evidence that parallel realities exist or that they can merge with our universe. The idea requires extra dimensions and exotic physics that have never been observed. Most physicists remain skeptical about such radical departures from established cosmology. Testing the theory poses enormous challenges. Baby universes interact with our reality only through gravity, making them essentially undetectable with current technology. Future gravitational wave detectors might potentially observe the space-time ripples created by universe mergers, but such observations would be incredibly difficult to distinguish from other cosmic phenomena. The implications extend far beyond cosmology. If baby universes constantly merge with ours, then reality is far more dynamic and interconnected than we imagined. Our universe represents just one bubble in an infinite foam of parallel realities, constantly growing through cosmic cannibalism. Critics argue that the theory simply replaces one mystery with another. Instead of explaining dark energy, it requires the existence of undetectable parallel universes with precisely the right properties to mimic dark energy effects. The theory may be mathematically elegant, but it lacks the observational foundation that supports more conventional models. Yet, the baby universe idea points toward an even more radical possibility about the nature of reality itself. Parallel realities may constantly interact with our universe, driving expansion through interdimensional forces we cannot comprehend. Beyond baby universe collisions lies an even more staggering possibility. Our expanding universe might be embedded within a vast multiverse where countless parallel realities influence each other through mechanisms that transcend ordinary physics. The expansion we observe could result from interactions between different versions of reality itself. Multiverse theories emerged from cosmic inflation models that predict exponential expansion continues forever in most regions of space. While inflation ended in our local patch 13.8 billion years ago, it persists elsewhere, creating infinite numbers of pocket universes with different physical properties. Each pocket represents a separate reality, with its own laws of physics. These parallel universes exist in higher dimensional space that encompasses our familiar three dimensions. Think of our universe as a three-dimensional sheet floating in a four-dimensional ocean. Other universe sheets drift nearby, occasionally bumping into each other or exchanging energy through dimensional boundaries we cannot perceive. Some theories suggest that dark energy emerges from interactions between our universe and nearby parallel realities. If other universes contain different amounts of matter and energy, gravitational effects could leak between dimensions, creating apparent acceleration in our space. The mysterious force we call dark energy might actually be gravitational influence from invisible parallel worlds. String theory, which attempts to unify all forces of physics, naturally predicts the existence of extra dimensions and multiple universes. In these models, our familiar particles and forces are confined to a three-dimensional membrane, while gravity can propagate through all dimensions. This could allow gravitational communication between parallel universes, even when other interactions remain impossible. The mathematical framework describing multiple universes reveals mind-bending possibilities. Some parallel realities might have stronger or weaker gravity than ours. Others could contain different types of particles or forces we have never imagined. The interactions between these diverse realities could create complex dynamics that drive cosmic expansion in ways that mimic dark energy. Eternal inflation models predict that new universes constantly spawn from quantum fluctuations in higher dimensional space. Our expanding universe might be influenced by the birth of neighboring realities, with each new universe creation affecting the geometry of the multiverse as a whole. This cosmic reproduction process could drive ongoing acceleration throughout all existing universes. The anthropic principle connects multiverse theory to cosmic expansion in profound ways. If countless universes exist with different expansion rates, we observe one with precisely the right properties to support complex structures like galaxies and stars. Universes that expand too quickly or too slowly cannot form the conditions necessary for life, so intelligent observers like us can only exist in universes with suitable expansion rates. However, multiverse theories face severe observational challenges. By definition, parallel universes remain beyond our ability to detect directly. We can only infer their existence through their supposed effects on our reality. This makes multiverse models extremely difficult to test using conventional scientific methods. Critics argue that multiverse theories are not science because they cannot be falsified through experiment or observation. If we cannot measure parallel universes or their effects, then their existence becomes a matter of mathematical speculation rather than empirical science. The theories may be mathematically elegant, but they lack the observational foundation that science requires. Some physicists propose that cosmic microwave background radiation might contain subtle signatures of collisions between our universe and neighboring parallel realities. These interdimensional impacts could create detectable patterns in the ancient light that fills our cosmos. Future telescopes with unprecedented sensitivity might potentially observe such multiverse fingerprints. The implications of multiverse-driven expansion extend to fundamental questions about the nature of existence itself. If our universe is just one bubble in an infinite foam of realities, then everything we consider unique about our cosmos becomes just one possibility among countless others. The expansion we observe represents a local phenomenon in a much vaster structure. Yet, proving these radical theories requires understanding the mathematical language that describes how expanding space actually works. Elegant equations reveal how the fabric of space-time stretches, carrying galaxies apart without moving them through space. Alexander Friedmann wrote down the mathematical description of cosmic expansion in 1922, 3 years before Edwin Hubble observed it directly. His equations, derived from Einstein's general relativity, predicted that the universe must either expand or contract. It cannot remain static, despite Einstein's initial belief to the contrary. The Friedmann equations describe how the scale factor of the universe changes over time. Think of the scale factor as a cosmic measuring stick that grows larger as space expands. If the scale factor doubles, then all distances double proportionally. A galaxy that starts 1 million light-years away ends up 2 million light-years away when carried along by the expanding measuring stick. The mathematics reveal that expansion depends on the total energy density of the universe. Matter and radiation create gravitational attraction that slows expansion down. Their density decreases as the universe grows larger, so their braking effect weakens over time. Dark energy creates gravitational repulsion that accelerates expansion. Its density remains constant, so its accelerating effect grows stronger as matter becomes more diluted. These competing influences create different expansion histories depending on which component dominates. In the early universe, radiation dominated and expansion decelerated rapidly. Later, matter took over, and expansion slowed more gradually. About 5 billion years ago, dark energy became dominant, and expansion began accelerating again. The metric tensor describes the geometry of space-time itself. In an expanding universe, the spatial part of the metric grows larger, while the time component remains unchanged. This mathematical structure captures how space stretches while time flows normally. Galaxies do not move through space. Instead, the coordinate system that defines space expands around them. Robertson and Walker extended Friedmann's work to describe universes with different geometries. Their metric applies to any universe that looks the same in all directions and at all locations on large scales. This cosmological principle allows the complex geometry of spacetime to be expressed using just one function, the scale factor, that depends only on cosmic time. The Hubble parameter quantifies how fast the scale factor changes at any given moment. It equals the expansion velocity divided by distance, creating the linear relationship that Hubble observed. The Hubble parameter decreases over time in matter-dominated universes, but remains nearly constant in dark energy-dominated universes. Redshift emerges naturally from the mathematical description of metric expansion. Light waves get stretched by the same factor that space expands during their journey. If the universe doubles in size while light travels from a distant galaxy, the wavelength doubles, and the light appears redshifted by a factor of 2. This cosmological redshift differs fundamentally from Doppler shifts caused by motion through space. The age of the universe can be calculated by integrating the Friedmann equations backward in time until the scale factor reaches 0. This integration accounts for how expansion rates have changed throughout cosmic history. The result gives 13.8 billion years for a universe with the observed densities of matter, radiation, and dark energy. Comoving coordinates provide an elegant way to describe positions in expanding space. In this coordinate system, galaxies that move only with the expansion remain stationary. Their comoving coordinates never change, even though their physical distances increase. This mathematical framework separates the effects of expansion from genuine motion through space. The critical density emerges from setting the Friedmann equations equal to 0. This represents the exact balance between gravitational deceleration and expansion velocity needed for the universe to expand forever, while gradually approaching 0 expansion rate. The critical density depends on the current expansion rate, explaining why it evolves along with cosmic expansion. Dark energy enters the equations through its equation of state, which relates energy density to pressure. Normal matter has 0 pressure, while radiation has positive pressure equal to 1/3 its energy density. Dark energy has negative pressure equal to minus its energy density, creating the gravitational repulsion that drives cosmic acceleration. The mathematical elegance of metric expansion contrasts sharply with our intuitive understanding of how space works. The equations describe a universe where distances change without objects moving, where space creates more space as it expands, and where geometry itself evolves over time. These concepts challenge our everyday experience while accurately predicting cosmic observations. Yet the mathematics reveal an even stranger truth about the universe, showing that expansion has no center and no edge. The universe expands everywhere at once, making every location appear to be the center, while having no actual center at all. Stand anywhere in the universe and look around. Every distant galaxy races away from your position in all directions. You appear to occupy the exact center of cosmic expansion. Move to any other galaxy and repeat the observation. From that new location, every distant galaxy also races away in all directions. That galaxy also appears to occupy the center of expansion. This cosmic illusion emerges from the uniform nature of space expansion. Because expansion affects all regions equally, every observer sees identical patterns of recession velocities. There is no preferred location in the universe, no special cosmic address that could claim to be the true center of expansion. The mathematics of metric expansion explain this centerless expansion. When the scale factor of space increases, every distance grows by the same percentage. Double the scale factor, and the distance between any two galaxies doubles. This uniform scaling has no center because it affects all locations identically. Picture an infinite sheet of graph paper where each square represents a galaxy. Now imagine stretching the entire sheet so that each square doubles in size. From the perspective of any square, all other squares appear to move away. Squares that started farther away end up even farther away after stretching. No square can claim to be the center of this stretching process. The balloon analogy illustrates the same principle in 2 dimensions. Draw dots on a deflated balloon to represent galaxies. As you inflate the balloon, every dot moves away from every other dot. From any dot's perspective, it appears motionless, while all others recede. There is no center to this expansion on the balloon's surface, because the expansion is intrinsic to the surface itself. Our 3-dimensional universe works identically, space expands uniformly in all directions from every point. This creates the illusion that each observer sits at the center of expansion, while actually demonstrating that expansion has no center at all. Every point in space participates equally in cosmic expansion. The absence of a center connects to the absence of an edge. If the universe had a center, it would also need boundaries where expansion originates or terminates. Instead, observations show that space looks the same in all directions on large scales. This cosmological principle implies that the universe either extends infinitely or curves back on itself without boundaries. Even if the universe has finite size, it would have no edge that we could identify. Just as you can travel around Earth's surface without finding an edge, you might be able to travel through a finite universe without encountering boundaries. The surface of a sphere has finite area, but no edge points. A finite universe could have finite volume, but no edge regions. The Big Bang did not happen at a specific location in space. Instead, it happened everywhere at once. The initial singularity was not a point in space, but rather a moment when all of space was compressed to zero size. As expansion began, every point in space participated equally in growing larger. There was no cosmic explosion from a central location. This concept challenges our everyday intuition about explosions and expansion. When a bomb explodes, debris flies outward from the explosion center into surrounding empty space. Cosmic expansion works completely differently. Space itself grows larger, carrying matter along for the ride. There is no surrounding empty space for the universe to expand into, because the universe contains all the space there is. The centerless nature of expansion also explains why we can see the cosmic microwave background radiation in all directions. This ancient light was emitted when the universe became transparent, 380,000 years after the Big Bang. We observe this radiation coming from every direction because every point in space participated in that moment of cosmic transparency. If expansion had a center, we would expect to see the cosmic microwave background concentrated in one direction where the expansion originated. Instead, the radiation fills the entire sky with remarkable uniformity, confirming that expansion affects all regions equally, without preference for any particular location or direction. The implications extend to the ultimate fate of cosmic expansion. Since there is no center or edge, acceleration affects the entire universe uniformly. Dark energy increases the expansion rate everywhere simultaneously, carrying all galaxies away from all other galaxies at ever-increasing speeds. This universal acceleration leads to a disturbing prediction about the future of everything that exists. Cosmic expansion will eventually spread all energy across infinite space, leaving the universe cold, dark, and lifeless forever. In 100 trillion years, the last star will burn out. The universe will enter an era of darkness that makes current cosmic time seem like an instant. Yet this represents only the beginning of an incomprehensibly long journey toward ultimate emptiness. Cosmic expansion ensures that the universe becomes colder and more dilute until nothing interesting can ever happen again. The second law of thermodynamics governs this cosmic death sentence. Entropy, or cosmic disorder, always increases over time. Energy spreads from hot regions to cold regions until everything reaches the same temperature. In an expanding universe, this process continues until all energy spreads across infinite space, creating a state of maximum entropy where no further work can be performed. Star formation will cease when the universe is about 1,000 times its current age. By then, expansion will have spread matter so thinly that gravity can no longer collapse gas clouds into new stars. Existing stars will continue burning until their fuel runs out, but no new ones will replace them. The era of stellar illumination will end permanently. As stars die, they leave behind white dwarfs, neutron stars, and black holes. These stellar corpses will drift through increasingly empty space as expansion carries everything farther apart. Eventually, Even gravitationally bound systems, like galaxies, will dissolve as the expansion of space overcomes their internal gravity. White dwarf stars will cool and fade over hundreds of trillions of years, becoming invisible lumps of crystallized matter drifting through the void. Neutron stars will cool even more slowly, taking longer than the current age of the universe multiplied by trillions to reach near absolute zero. These cosmic embers will represent the last warm objects in an increasingly frigid universe. Black holes will survive longer than any other structures, but even they face inevitable doom. Stephen Hawking showed that black holes slowly evaporate by emitting radiation, losing mass over unimaginably long timescales. A black hole with the mass of our Sun would take longer to evaporate than the number represented by 1 followed by 67 zeros years. The largest black holes, those containing billions of solar masses, will persist for time so long that writing the number of years would require more digits than there are atoms in the observable universe. Yet even these cosmic monsters will eventually surrender all their mass to Hawking radiation, leaving behind nothing but elementary particles scattered across infinite space. After the last black hole evaporates, the universe will contain only electrons, positrons, neutrinos, and photons spread across vast distances. These particles will be so far apart that they rarely interact. The temperature of space will approach absolute zero as expansion dilutes the cosmic microwave background radiation to infinitesimally low energy levels. Even protons, the building blocks of atomic nuclei, may not survive forever. Some theories predict that protons decay over timescales that dwarf even black hole evaporation. If true, then all matter will eventually dissolve into lightweight particles like electrons and neutrinos. The expanding universe will become a thin soup of elementary particles with essentially no interactions between them. The final state represents maximum entropy, where energy spreads so uniformly that no temperature differences exist. Without temperature gradients, no engines can operate and no work can be performed. The universe reaches thermodynamic equilibrium, a state of perfect cosmic boredom where nothing ever changes. This heat-death scenario assumes that dark energy remains constant over time. If dark energy grows stronger, it could lead to an even more dramatic ending called the Big Rip. In this scenario, accelerating expansion eventually overcomes all forces, tearing apart galaxies, stars, planets, and ultimately atoms themselves. The universe would end not in gradual cooling, but in violent dismemberment of all structures. Alternatively, if dark energy weakens or reverses, cosmic expansion could slow down, or even reverse into contraction. This would lead to a big crunch where all matter and energy collapses back into a singularity, potentially starting the cycle over again with a new Big Bang. Current observations suggest that dark energy remains nearly constant, favoring the heat-death scenario over more dramatic alternatives. The universe appears destined for a cold, empty future where expansion carries everything so far apart that meaningful events become impossible. Yet beyond our cosmic horizon lie regions of reality that expansion has already carried beyond our reach. Infinite regions of reality exist forever beyond our reach, containing wonders and terrors we can never observe or understand. 46 billion light-years away, in every direction, lies the edge of everything we can ever know. Beyond this cosmic horizon, expansion carries space away faster than light can travel toward us. These unreachable regions might contain impossible civilizations, alternate physics, or even copies of ourselves living identical lives in parallel cosmic domains. The observable universe represents just one bubble in a potentially infinite cosmos. If space extends forever beyond our horizon, then it contains infinite galaxies, infinite stars, and infinite planets. Somewhere in these unreachable realms, identical copies of Earth orbit, identical copies of our Sun, populated by identical copies of every person who has ever lived. This cosmic repetition emerges from basic mathematics. Any finite system has only a limited number of possible configurations. If space is truly infinite, then every possible arrangement of matter and energy must occur somewhere. Your exact configuration of atoms exists in countless locations throughout the unobservable universe, experiencing identical thoughts and memories at this very moment. The cosmic horizon moves outward at light speed, revealing new regions of space every second. However, dark energy acceleration ensures that distant matter recedes faster than the horizon expands. The total number of galaxies within our observable bubble actually decreases over time, despite the horizon growing larger. More galaxies disappear beyond our reach than enter our visible domain. Future civilizations will inhabit a lonelier cosmos. As expansion accelerates, galaxy after galaxy will vanish beyond the cosmic horizon until only our local gravitationally bound group remains visible. Our descendants will see a universe containing just dozens of galaxies instead of the trillions we observe today. They will have no way to know that countless others once filled their sky. The regions beyond our horizon might operate under completely different physical laws. If cosmic inflation created multiple domains with different properties, then distant regions could have different constants of physics, different numbers of spatial dimensions, or different types of particles and forces. These alternate physics domains remain forever hidden from our observations. Some of these regions might have stronger gravity that prevents expansion from occurring at all. Others might have weaker gravity that allows expansion to proceed much faster than in our domain. Still others might lack dark energy entirely, leading to very different cosmic histories. The diversity of possible physics creates an infinite library of cosmic experiments we can never read. Advanced civilizations might exist in these unreachable regions. They could have developed for billions of years longer than us, achieving technologies that manipulate space and time in ways we cannot imagine. These cosmic superintelligences might have solved problems that perplex us, discovered physics beyond our theories, or even learned to communicate across cosmic horizons through methods we have never conceived. Conversely, these distant regions might contain cosmic horrors that dwarf anything in our observable universe. Black holes larger than our entire solar system could consume galaxies whole. Vacuum decay events could propagate through space at light speed, destroying all matter and energy in their path. Reality warping phenomena could make the laws of physics themselves unstable and dangerous. The multiverse theories suggest that beyond our cosmic horizon lie not just distant regions of our space, but entirely separate universes with their own spacetimes. These parallel realities exist in higher dimensional space that encompasses our familiar three dimensions. Each universe evolves independently, following its own physics and expansion history. Some of these parallel universes might be mirror images of ours, with identical physics but opposite characteristics. Others might have completely alien properties that make our reality seem mundane by comparison. The total collection of all possible universes, called the multiverse, could contain infinite diversity of cosmic possibilities. However, the existence of these unreachable regions raises disturbing questions about the nature of scientific knowledge. If we can never observe or test theories about what lies beyond our horizon, can we truly claim to understand the universe? Science depends on observation and experimentation, but cosmic expansion places absolute limits on what we can ever hope to observe. The cosmic horizon represents the ultimate boundary of human knowledge, yet it expands our perspective on cosmic expansion to reveal even more mysteries about why space itself accelerates. Dark energy grows stronger over time, driving cosmic expansion at ever-increasing rates toward an unknowable destiny. Logic suggests that cosmic expansion should slow down. All the matter in the universe creates gravitational attraction that pulls everything together. This cosmic braking force should gradually overcome the initial expansion velocity from the Big Bang, eventually bringing expansion to a halt. Instead, observations reveal the opposite trend. Expansion accelerates relentlessly, driven by dark energy that overpowers gravity on cosmic scales. This acceleration began about 5 billion years ago, when the universe was roughly half its current age. Before this cosmic transition, expansion indeed slowed down as expected. Matter density was high enough that gravity dominated over dark energy, causing the expansion rate to decrease steadily. Then, dark energy gained the upper hand, and acceleration has continued ever since. The crossover happened because matter density decreases as the universe expands, while dark energy density remains constant. In the early universe, matter was packed closely together, creating strong gravitational fields that slowed expansion. As space grew larger, matter spread out, and its gravitational influence weakened. Meanwhile, dark energy maintained constant density, eventually becoming the dominant force. Current observations suggest that dark energy accounts for about 68% of the universe's total energy budget. This percentage will continue growing as matter becomes more dilute. In the future, dark energy will dominate the universe even more completely, driving acceleration to unprecedented rates. The Dark Energy Spectroscopic Instrument has detected hints that dark energy might be evolving over time rather than remaining constant. If confirmed, this discovery would revolutionize our understanding of cosmic acceleration. Dark energy that changes over time could lead to dramatically different futures than models with constant dark energy predict. If dark energy grows stronger over time, cosmic acceleration will intensify until it overcomes all other forces in the universe. This scenario, called the Big Rip, would tear apart every gravitationally bound structure. First, galaxy clusters would disperse as dark energy overcomes their gravitational binding. Then, individual galaxies would dissolve as stars scatter across expanding space. The Big Rip timeline depends on how rapidly dark energy strengthens. Conservative estimates suggest that galaxy clusters will unbind in about 20 billion years. The Milky Way galaxy would dissolve 60 million years later. Our solar system would break apart just minutes before Earth itself gets torn apart by dark energy forces stronger than the electromagnetic bonds holding atoms together. Alternatively, if dark energy weakens over time, cosmic acceleration could slow down, or even reverse. This would lead to a very different future, where expansion eventually stops and the universe begins contracting. Such a scenario could end in a big crunch, where all matter and energy collapse back into a singularity, potentially triggering a new Big Bang cycle. Some theoretical models predict that dark energy oscillates over cosmic time, alternately accelerating and decelerating expansion in endless cycles. These cyclical universe models suggest that our current acceleration phase represents just one epoch in an eternal sequence of cosmic expansions and contractions. The universe could experience infinite cycles of birth, growth, and rebirth. The accelerating expansion affects the fundamental structure of space and time. As dark energy dominates more completely, it creates an exponentially expanding space-time geometry, similar to cosmic inflation. Future expansion might approach the incredible rates that occurred during the first fraction of a second after the Big Bang. This accelerating expansion will eventually isolate our local group of galaxies from the rest of the observable universe. Dark energy will carry all other galaxies beyond our cosmic horizon, leaving us in an island of matter surrounded by empty, exponentially expanding space. Future astronomers will have no evidence that billions of other galaxies once filled their sky. The acceleration also affects the cosmic microwave background radiation, stretching its wavelength to ever lower energies. Eventually, this primordial radiation will be redshifted into radio waves, then infrared, and finally to wavelengths so long that they become undetectable. The universe's baby picture will fade away as expansion dilutes its energy below the threshold of observation. Even more mysteriously, the acceleration connects to quantum mechanics in ways we do not fully understand. Dark energy might emerge from the quantum properties of empty space itself, representing a fundamental feature of reality rather than a temporary cosmic phenomenon. Yet dark energy is not the only invisible component driving cosmic evolution, as another mysterious substance shapes the very structure of expanding space. Invisible matter, 5 times more abundant than ordinary atoms, shapes cosmic expansion by creating the scaffolding on which galaxies form. While dark energy drives cosmic acceleration, dark matter controls how expansion affects the formation of cosmic structures. This invisible substance makes up 27% of the universe, outweighing ordinary matter by a factor of more than 5 to 1. Yet, dark matter interacts with nothing except gravity, making it completely transparent to light and impossible to detect directly. Dark matter reveals itself through gravitational effects on cosmic expansion patterns. In regions where dark matter concentrates, its gravity slows down the local expansion rate. This creates slight variations in cosmic expansion that allow matter to clump together into galaxies and galaxy clusters. Without dark matter, expansion would proceed so uniformly that no large structures could ever form. The cosmic microwave background radiation shows tiny temperature fluctuations that map where dark matter concentrated when the universe was only 380,000 years old. These ancient density variations grew over billions of years as dark matter's gravity attracted ordinary matter into the same locations. The result is the cosmic web of galaxies and galaxy clusters we observe today. Dark matter particles remain completely mysterious despite decades of searches. They cannot be ordinary atoms because atomic matter would create observable effects in the cosmic microwave background that we do not see. They cannot be photons or neutrinos because these particles do not clump together gravitationally. Dark matter must consist of unknown particles that interact only through gravity. Leading candidates include exotic particles predicted by theories that extend the standard model of particle physics. Weakly interacting massive particles, called WIMPs, could have the right properties to form dark matter. These hypothetical particles would be produced in the early universe, but interact so weakly with ordinary matter that they remain undetectable except through gravitational effects. Alternative theories propose that dark matter consists of primordial black holes formed in the early universe, sterile neutrinos that barely interact with anything, or axions that emerge from quantum field fluctuations. Each possibility requires different physics and would affect cosmic expansion in subtly different ways. The distribution of dark matter creates a cosmic scaffolding that guides how expansion shapes the universe. Dark matter forms vast filaments stretching across hundreds of millions of light years, connected by dense nodes where galaxy clusters form. This invisible architecture determines where galaxies can form and how they evolve over cosmic time. In regions with high dark matter density, expansion slows down enough to allow gravity to overcome cosmic growth. Gas clouds can collapse to form stars and galaxies. In regions with low dark matter density, expansion proceeds too rapidly for gravitational collapse. These cosmic voids remain nearly empty, as expansion carries away what little matter they contain. Dark matter also affects how individual galaxies rotate and evolve. The invisible matter creates gravitational wells that hold galaxies together as cosmic expansion tries to pull them apart. Without dark matter's gravitational binding, galaxies would disperse as expansion overcomes the gravitational attraction of their ordinary matter alone. Computer simulations show that dark matter forms complex structures on all scales, from galaxy halos to cosmic filaments. These dark matter structures grow over time through gravitational attraction, while cosmic expansion carries different structures farther apart. The interplay between dark matter clustering and cosmic expansion creates the hierarchy of structures we observe. The relationship between dark matter and dark energy creates a cosmic competition that determines the future of structure formation. Dark matter tries to build larger structures through gravitational attraction, while dark energy prevents this by accelerating expansion. As dark energy becomes more dominant over time, it will eventually halt all structure formation permanently. In the far future, dark energy will completely overcome dark matter's gravitational influence. No new cosmic structures will form, as expansion accelerates beyond the point where gravity can collect matter together. The dark matter scaffolding will become irrelevant in a universe dominated by exponential expansion. Current galaxy surveys map dark matter distribution by observing how its gravity bends light from distant galaxies. These gravitational lensing measurements reveal dark matter's role in shaping cosmic expansion at different times throughout the universe's history. The patterns confirm that dark matter clustering has remained crucial for structure formation throughout cosmic evolution. Yet, even dark matter represents just one component in a cosmic inventory that spans scales from the quantum realm to infinite space itself. From quantum fluctuations smaller than atoms to cosmic structures spanning billions of light years, expansion connects the tiniest scales of reality to the infinite. Space expansion operates across a range of sizes that defies human comprehension. At the smallest scales, quantum fluctuations create virtual particles that pop into existence and disappear in less than a trillionth of a trillionth of a trillionth of a second. At the largest scales, cosmic expansion carries galaxy clusters across distances measured in billions of light years over billions of years. The Planck length represents the smallest meaningful distance in physics, measuring about 1 followed by 34 zeros smaller than a meter. Below this scale, quantum effects make the concept of distance itself meaningless. Yet cosmic inflation stretched quantum fluctuations from Planck-scale ripples to galaxy-scale density variations, connecting the smallest possible physics to the largest observable structures. Atomic nuclei measure about 100,000 times larger than the Planck length, while atoms extend 100,000 times larger than nuclei. Yet, cosmic expansion has no effect at these tiny scales because electromagnetic and nuclear forces completely overwhelm the weak gravitational effects that drive space growth. The forces holding your body together are trillions of times stronger than cosmic expansion's influence. Planetary systems, like our solar system, span distances about 1 trillion times larger than atoms, but gravity still dominates over expansion. The Sun's gravitational field keeps Earth in orbit despite the universe expanding around us. Expansion affects only the vast empty regions between star systems, where gravity becomes too weak to resist cosmic growth. Our galaxy measures about 100,000 light-years across, containing roughly 400 billion stars held together by gravity. The Milky Way represents a gravitationally bound island in expanding space. While the universe grows larger around us, our galaxy maintains its size and structure because its internal gravity overwhelms the weak effects of cosmic expansion. Galaxy clusters span about 10 million light-years and contain hundreds of individual galaxies bound together by gravity. These represent the largest gravitationally bound structures in the universe. Beyond this scale, cosmic expansion dominates over gravity, carrying different galaxy clusters farther apart over time. The cosmic web extends across hundreds of millions of light-years, connecting galaxy clusters through vast filaments of dark matter and ordinary matter. This represents the largest coherent structure in the universe. The web formed as cosmic expansion stretched early density fluctuations, while gravity amplified them into the patterns we observe today. Cosmic expansion affects different scales in dramatically different ways. At quantum scales, expansion might create new virtual particles through quantum field effects in curved spacetime. At atomic scales, expansion has essentially no effect because other forces dominate completely. At galactic scales, expansion provides a gentle background influence that affects long-term evolution. At cosmic scales, expansion controls the overall geometry and fate of the universe. The observable universe spans about 93 billion light-years in diameter, representing the largest region we can ever hope to study. This cosmic sphere contains about 2 trillion galaxies, each containing billions of stars. Yet, this observable volume might represent an infinitesimally small fraction of the total universe if space extends infinitely beyond our cosmic horizon. If the universe is truly infinite, then cosmic expansion operates on scales that exceed even our ability to conceptualize. Infinite space contains infinite matter and energy, all participating in the same expansion process that affects our local cosmic neighborhood. The same physical laws that govern expansion in our observable region apply throughout infinite realms we can never observe. The hierarchy of cosmic scales reveals how expansion connects all levels of physical reality. Quantum fluctuations in the early universe provided the seeds for cosmic structure formation. These microscopic variations grew into galaxies and galaxy clusters through the interplay between gravity and expansion. Dark energy now dominates the largest scales, driving future expansion toward unknown destinies. Timescales in cosmic expansion span equally incomprehensible ranges. Quantum fluctuations occur in time so brief that light cannot cross a proton during their duration. Cosmic expansion began 13.8 billion years ago and will continue for times that dwarf the current age of the universe by factors too large to write down. The ultimate scale of cosmic expansion might extend beyond our universe entirely. If multiverse theories prove correct, then our expanding space represents just one bubble in a higher dimensional realm containing infinite other universes. Each universe expands independently, creating an infinite hierarchy of expanding realities nested within expanding realities. Yet, across all these scales, from quantum foam to infinite multiverse, expansion poses one fundamental question about humanity's place in the cosmic story. What does it mean to exist in a universe that expands into nothing while carrying everything we know toward an uncertain destiny? We began with the question of what the universe expands into. The answer reveals something profound about reality itself. The universe expands into nothing because it contains all the space there is. Space creates more space as it grows, like a cosmic magic trick that conjures its own stage. This expansion carries every atom in your body, every star in the sky, and every galaxy across the cosmos on a journey toward an unknown future. You are made of rare stuff. The atoms that form your body, your planet, and everything you can touch represent less than 5% of reality. The remaining 95% consists of dark matter and dark energy that we cannot see, touch, or understand. You exist as a temporary arrangement of minority particles in a universe dominated by invisible forces. Your existence depends on cosmic expansion happening at exactly the right rate, too fast, and matter could never have clumped together to form galaxies and stars. Too slow, and the universe would have collapsed back into a singularity before life could evolve. The expansion rate balances on a knife's edge that permits complex chemistry, stellar evolution, and biological development. Every breath you take participates in cosmic expansion. The space between your atoms grows infinitesimally larger with each passing moment, though forces holding you together easily overcome this cosmic stretching. You remain intact while riding the expansion of space-time itself toward destinations no human mind can fully comprehend. The light reaching your eyes tonight began its journey billions of years ago when the universe was younger and smaller. You see ancient history stretched by cosmic expansion into the colors that paint the night sky. Every star appears redshifted by the growth of space during its light's cosmic voyage. You observe the universe's past while participating in its expanding present. Your cosmic address sits in an expanding galaxy, in an expanding cluster, in an expanding universe that might itself be expanding within higher dimensional realms we cannot perceive. This nested hierarchy of expansion places you at the center of your own observable cosmic sphere, while making you utterly insignificant in the potentially infinite scope of total reality. The expansion that began 13.8 billion years ago will continue for times that make the current age of the universe seem like an instant. Long after our sun dies and our galaxy disperses, cosmic expansion will carry the remnants of everything we know across distances that dwarf today's observable universe. The atoms that once formed your thoughts will drift through a cold, dark cosmos approaching absolute zero. Yet perhaps this cosmic perspective offers strange comfort. You exist during the universe's most interesting epoch, when stars shine brightly and galaxies dance across cosmic distances. You participate in expansion's story during the brief moment when complex structures can form and persist. Your existence represents a temporary victory of organization over the cosmic trend toward increasing entropy. The mystery remains unsolved. We know that space expands, carrying galaxies apart at accelerating rates driven by dark energy we do not understand. We know this expansion began with the Big Bang and will continue toward heat death or cosmic rip. We know the mathematics that describe expansion and the observations that confirm it, but we still do not know what expansion truly means for the nature of existence itself. Perhaps the answer lies not in understanding what the universe expands into, but in recognizing that you expand along with it. Every moment of your life unfolds against the backdrop of cosmic growth. You think, dream, and create meaning, while space itself grows larger around you. Your consciousness represents one of the universe's ways of experiencing its own expansion. The ultimate question transcends physics and touches philosophy. If the universe expands into nothing while containing everything, what does this say about the nature of existence, consciousness, and meaning? You find yourself in an expanding cosmos that defies intuition while following precise mathematical laws, temporary yet part of an eternal cosmic story. In the end, cosmic expansion connects you to the deepest mysteries of reality, while reminding you that existence itself represents the most remarkable phenomenon in the universe.